Good day to everyone, and thank you all for joining us for our live webinar, which will be presented by our guest speaker, Professor Laura Goracci, and entitled Computational Strategy for Unveiling Low Abundance Lipids from Epilipids to Click Chemistry Derivatives. My name is Maria Fedorova, and I'm based at TU Dresden in Germany, and I will be your host for today. The webinar will be around 45 minutes, allowing 10 minutes at the end for the question. And let me introduce our speaker for today. Laura Goracci is a full professor of organic chemistry at the University of Perugia in Italy. In 2004, she obtained her PhD in chemical sciences from University of Perugia and her PhD in organic chemistry from University of Bordeaux as a part of joint degree program. From 2008 to 2011, Laura worked at multivariate informametric analysis company, collaborating with the software company Molecular Discovery, and leading projects with several major pharmaceutical companies. In 2011, she returned to academia, where her research focused on developing models to understand structure-activity relationship by generating in-house data, as well as designing chemoinformatics workflow pharmaceutical applications. In this context, she also led the design and development of the LipidsStar and Mars software's platform for untargeted lipidomics and metabolomics, and continues to collaborate with pharmaceutical and software companies. She has placed particular emphasis on the development of in silico workflows for detection and annotation of low abundance species, so I guess we will hear about that today, and served as a working group leader for epilipidomics analysis and data integration strategy within the EpilipidNet cost action.
Hello everyone, and thank you, Maria, for the kind introduction. I would also like to thank Lorraine and Lipid Maps for this opportunity to contribute to the Lipid Maps webinar series. So, as Maria said, today's webinar will illustrate computational strategies for unveiling low abundance lipids. But before starting, let me tell you a few words about my work as a cheminformatician in lipidomics. My work often begins with requests from members of the lipidomics community who seek support for facilitating data analysis in innovative experimental settings. Therefore, I start identifying potential solutions and I try to define step-by-step workflows that might be of general interest. Today, computational tools for lipidomics are widely used, and numerous software and computational tools have been developed to support lipidomics, especially untargeted lipidomics. With the number of software, also the complexity of this software platform has increased in the recent years to keep up with instrumental and analytical advancements. However, for researchers, sometimes it is challenging to select which approach best suits a given application. And to try to help the lipidomics community, a few years ago, researchers working in the field of developing computational tools for lipidomics have joined their effort to make a review of the state-of-art computational tools available, especially for untargeted lipidomics. We tried to cover data conversion and integration, statistical analysis and visualization, quantification and identification. And the outcomes of this detailed research is the base of the lipidomics tool guide, which is freely available in the Lipid Maps website. So, since my work usually starts with requests, one of the recurring requests I have received over the past 10 years can be summarized as follows. I am planning to run a CMS-based untargeted lipidomics analysis, and I need to focus not only on the classical high-abundant lipids, but also on the low-abundant ones. At the same time, I need software that is not a black box. Nobody loves black boxes. Fast in processing and annotation, and also applicable to different experimental scenarios, because if we are developing something that is very rigid, probably it will be already old in a couple of months. Therefore, we need flexibility. The interest in low-abundant species is likely clear to this audience, as they include not only natural molecules that are involved in signaling, but also modified lipids like the epilipids, and also species that are formed to trace biological pathways like stable isotope-labeled species or derivatized lipids. Therefore, today I'm going to divide my webinar in two parts. The first part is focused on strategies for data processing. That will cover the importance of the settings for threshold and gap filling tools, IO mobility support, and trend analysis. In the second part of the webinar, I will focus on identification strategies with example for stable isotope-labeled lipids, epilipids, and derivatized lipids, specifically click chemistry derivatives. Regarding data processing, new instrumentation has led to increased sensitivity, mass accuracy, and resolving power. And in addition to that, in the recent years, new analytical workflows have been developed to try to increase the range of lipids that can be analyzed in a single run. As a result, we are now able to generate huge amount of data during a classical untargeted lipidomics approach. And we will have our lipidome composed of elephants, so high abundant species, and mice, low abundant species, which are sometimes covered by noise. We say that it's obvious that data processing really plays a pivotal role to try to get only the information we want and remove everything is noise, because processing noise will be extremely time-consuming. There are several software that have different algorithms that are connected in order to make data processing. So now I'm going to refer to LipoStar. That is a software that was developed to support LCMS untargeted lipidomics. In our setting, we start converting instrument data files. So the first step is conversion. And then converted files go through several algorithms. The most important ones are feature detection, retention time correction, alignment, and noise reduction. Of course, there are many more, some which are mandatory and some others which are just optional. At the end of this process, the data will be organized in a kind of fat data matrix. It is fat due to the large capability in getting peaks within the new instrumentation. So usually the number of the columns is much higher than the number of the samples we have. And we will immediately see that this data matrix contains several empty cells. These empty cells are not real missing values. This is very important to understand the role that data processing might have in detecting low abundant species. Indeed, sometimes these missing values are actually values that are below the processing threshold. And this, of course, occurs much more often for low abundance lipids. So how can we try to reduce the number of these empty cells? Before going in the solutions and the potential solution, we have to understand how critical is the setting used for as a threshold to remove the noise during data processing. Let's imagine that these blue peaks are one feature across the different samples in our data matrix. If we apply a high processing threshold, many of them will probably be removed, and this is the effect we are going to have in our matrix. So this is our column. This will have an effect even in the statistical multivariate analysis, in multivariate statistical analysis, because we are applying scaling factors, and this will have an impact in that. But if we go using low processing threshold, we probably will have a very fat data matrix, but the columns will be more continuous in values, as you see here. and the image that we get in our scores plot will be probably very different from the first case. In this specific example, I'm showing that there is a better separation in the case that we use a low processing threshold, and this would be a sign that probably we excluded important features at the beginning. But I mean, there is also the risk to get more noise. Another problem we must be aware of is that when we really do not control the processing threshold, and we have columns like this, in which the few values which are present are only from one class of our compounds, our samples. In this case, this is a very dangerous case because these variables might become potential high leverage variables, although there is not a real biological meaning. Therefore, my first advice is to test several options for processing threshold, especially when we are interested in low abundance lipids. But there are other solutions. In LipoStar and in MZMine and probably in other software, there is the option to use kind of gap filling algorithms to reduce the number of empty cells in your data matrix. This can be done during the data processing step, and this algorithm can vary a little bit one from the other. I am presenting here the one we developed in LipoStar, but the meaning is always the same. We want to discriminate between what is noise and what is a low abundant peak. That might be a peak that is with low intensity in one sample, although in other sample is above the threshold. Since in LipoStar we have two steps, the conversion of the files from the instrument data files and the real processing threshold and data analysis, we can start in a conversion with a very low threshold just to remove the noise, what is really noise, and then we can apply a higher threshold for processing. This means that only the features here with an intensity that is higher of the processing threshold, at least in one sample, will be transformed in columns in the data matrix. Once the data matrix is done, so we tried to remove everything might be noise, the gap filling action will work going back to the data matrix, re-inspecting all the missing values and see if for this sample here, for example, in this point, there was actually a peak that was not included in the data matrix just because it was slightly below the processing threshold. In this way, we are making our variable more continued, but without increasing the number of variables with noise. There are, of course, other strategies to try to facilitate the detection of more low abundance species. And if we look at the literature, there is an increasing interest in ion mobility to try to resolve and discriminate between noise peaks and low abundance peaks. The increasing interest in ion mobility resulted also in an increased interest in developing solutions for ion mobility. And we also did our part. This is an example on how software is expected to work because the user wants to see the peaks, wants to see the mobilogram. And we also needed to develop a completely new 3D peak detection algorithm and allow the 3D reintegration of the peaks if the user has this specific need. The ion mobility was also tested for epilipids, for example. There is the reference here. And the result of the study was that for sure, it can be very useful, but still not all the issues are solved. So for a matter of time, I'm not going to talk about the details, but if you are interested, I have a reference for that. To conclude this first part, I would like to spend a few words about trend analysis. Trend analysis is an approach that is widely used in pharmaceutical companies for biomarker discovery. In a nutshell, the trend analysis allows the user to filter features by matching with a desired trend. That is usually the trend that is the ideal trend for a biomarker. This filtering can be applied prior to any annotation and disregarding abundance. We developed the trend analysis in Lipostar in collaboration with Dr. Alaclos in Sanofi, who shared some data and knowledge to test what we were doing. And basically, that was the first example she provided us in a slide. So she said that an ideal biomarker having to monitor patients' groups would be, for example, something that increases with disease state and decreases with treatment doses. So in order to monitor this kind of biomarkers, we would need to label our samples based on these classes, these 7 classes, and extract all the features that match this trend. This is a very complex case, but actually we could also apply biomarker, the trend analysis to hypothesis-driven time course studies. So maybe we want to extract all the species that are increasing over the time or decreasing over the time. And the annotation will be done only on this small subset of features that can match a trend. What is the benefit here? The time-consuming processing step that occurs when we try to lower the processing threshold can be balanced by the reduced features that need to be annotated. So we are wasting more time in the processing, but we are saving time in the annotation. And we could also expect that this is a good way to reduce the noise, because if we work with quite complex trends, it is unlikely that noise will match that desired trend. So we can really try to fish low abundant species that might be biomarkers. So said that, I have concluded the first part about data processing strategies, and let's start talking about identification strategies. Before talking about the 3 classes of compounds that are the major topic of this webinar, we have to say that in order to have a good identification, we need to maximize MSMS information for low abundance lipids. Here there are experimental strategies that can be applied, and probably one of the most widely used is the application of data-dependent acquisition with automatic exclusion list generation to try to get the maximum number of MSMS spectra also for low abundant species. This approach will provide a massive amount of information, but it will take more time for that analysis, and there is always the risk that the most intriguing compounds actually in the end lack of MSMS data. So the first solution we can provide as developers of a computational solution is to at least allow to re-import MSMS spectra when needed without reprocessing all the files. There is also a debate if data-independent acquisition might be a good alternative. There are more and more studies coming out with data-independent acquisition, and I am not an analytical chemist, so I'm not aware on how good would be working on low abundant species in DIA, but from the computational perspective, I can see that the number of software tools that are now supporting data-independent acquisition is increasing. And the picture I'm showing here, it's now quite old, and I know for sure that some of the software reported here in the bottom already moved and improved to support also DIA. So that would be another strategy that can be used thanks also to the computational improvements. Concerning the different identification methods that we can apply, they can be classified classically in spectral matching, top-down, and bottom-up approaches. If we look the input that we need in order to run these identification methods, you will see highlighted in red the word libraries and structured databases. This might be a problem when we are going to annotate low abundance species, because first of all, sometimes we have a lack of experimental libraries due to the fact that there is a lack of standards to generate these libraries, especially for some of the classes I'm going to talk today. And the other problem is the in silico generated libraries that usually make use of fragmentation rules. But again, to develop fragmentation rules, we need standards and we need experimental data. So sometimes this is not the best way to go unless you are not working heavily to have standards or data for deriving experimental rules. For top-down approaches, again, the problem is the use of structured databases, and I will tell you in a few minutes about the problem of the combinatorial explosion we might have. In order to better understand the examples that I'm going to show in the next slides, I have to tell you something about the classical annotation module that is present in the LipoStar software. LipoStar makes annotation based on spectral matching approaches as a major route of identification, and has a list of fragmentation rules for the different classes and subclasses already coded in the software for the different acquisition modes and different adducts. So since we have fragmentation rules, we need structures to be fragmented to generate a database of fragmented lipids. These structures can be imported in SDF format, and to not reinvent the wheel, many years ago, we decided to accept only the SDF format that is already used in the lipid maps database, in the LMSD database, to be more precise. So you can generate this SDF file as you like, or you can download the structures from lipid maps, but you also have the lipid builder, which is a module that allows you to combine in silico the different building blocks of lipids. And once the SDF file is automatically generated with all the tags we need, these structures can be fragmented to generate the database. In the database, if needed, one can also add experimental data. The database can be also enriched by adding retention time and CCS values to support ion mobility identification. Once the database is ready, that will be stored and always there, and in each session, in each run, you can use it for identification with the classical spectral matching approach. And the database is also trainable, so unknown features can be manually annotated and re-added in the DB. This is the classical way to work. But what happens if we want to use the same module for the low abundant lipid class I was mentioning you before? For stable isotope-labeled lipids, what we are going to have is that we need definitely a different structured database, because we need to generate a database with labeled species. But at least we can use the same fragmentation rules, because rules are not expected to change. While for epilipids and derivatized lipids, like in click chemistry, not only the structure DB changes, but also the fragmentation rules. And this is the major issues, as I was telling you, because the engine will work only if we provide this kind of information. So let's go to the stable isotope-labeled lipids. This part of my studies, again, started with a specific request. The request was from Professor Guido Franzoso at the Imperial College, UK, in 2018. And he came to me with a kind of, for me, quite complex experimental design to investigate the triacylglycerol metabolism in terms of lipogenesis and lipolysis, to study the effect in aggressive colorectal carcinoma. I'm not going into detail about this study that was published, so all the details are there, but I will focus on the computational solution I could find. So focusing now in the pulse chase experiment, they treated their cells with U13C oleic acid, and they asked me to try to monitor as a proof of concept not only the oleic acid inglobated in complex lipids, but also possible results of elongation and desaturations. So what could we do? Having this engine that I was already showing before, the idea was simply to improve the lipid builder module, allowing to add chains according to a given experimental design. In this case, allowing generating structures of fatty acids that were labeled, and considering also the possibility to modify them for elongations and desaturations. We did this, and with this improvement, we combined some derivatives that could come from this fatty acid, labeled fatty acid. We consider several different classes and subclasses, and with this small proof of concept work, we were able to generate a database of 48,000 lipids and more than 240,000 spectra, because we consider the different adducts and the different acquisition mode, positive and negative acquisition mode. And with that, we were able to identify these labeled species. The most useful part of this solution was that we could analyze at the same time unlabeled lipids and labeled lipids, because in the same session, in the same processing, we simply needed to change the database for the annotation, and this allowed us also to compare which nodes in the biopathways were highlighted in one scenario and in the other one. So in the end was a quite simple case, because here we do not need to change any fragmentation rule. But now let's go to epilipids. Here, as I was already anticipating, we need a different DB, and we also need the different fragmentation rules. And not always we have all the standards we need to make this work. We can generate virtual libraries of epilipids. It is something that is challenging, but not impossible. And as a proof of concept, I can show you this work we made in collaboration with Professor Rosario Dominguez at the University of Aveiro. My former PhD student, Stefano Bonciarelli, spent 6 months in Rosario's lab. And the idea was to try to identify nitro-oxidized lipids. We tried to do a database of fragmented nitro-oxidized lipids, but we needed to work on the generation of a DB and in the definition and the coding of fragmentation rules. For the database, we only consider a few classes, PC, PE, PS, and PI, a few chains in SN1 position, SN2 position, and the modification in SN2 that were nitration, double nitration, and nitration plus hydroxylation. With this small subset, we obtained more than 2,000 potential nitro-oxidized lipid as a structure. and you start having an idea of the combinatorial explosion with respect to the classical lipids which are in the databases. But that was only the first part. Then we needed to go back to the literature and the studies that were already done at the University of Aveiro, code all the fragmentation rules, added this in the DB Manager, and in this way we were able to make the virtual library that was used in different publications. The nitro-oxidized lipid project was a project that aimed at showing that the use of a DB was not impossible. But actually, for oxidized lipids, we decided to test and try different solutions. NI at the University of Dresden, TU Dresden, made an estimation of the epilipids, only considering some oxidized species. And to show you what is just below the iceberg, he first tried to make all the potential modification in all possible position with permutation and repetitions and so on. And he came up with 10 at the 12 enumerated modified lipids. So really a huge number. The first idea we could have, of course, would be to use knowledge-based constraints to reduce this number. But still, what we are going to have is in the order of 10 at the 4, 10 at the 5. Therefore, making a database, generating a database of all the knowledge-based, potentially accepted oxidized lipids, it's quite challenging. And this is why we decided not to go directly in the generation of a database. Which are other alternatives possible? In our work within the EpilipidNet consortium in the construction, we tried as a working group devoted to epilipidome to review all the software tools that were proving the presence of algorithms for oxidized lipids. And we tried to understand which were the principal challenges. We came up with 5 challenges: low abundance, high structural diversity, large number of isomers and isobars, different fragmentation compared to native lipids, and nomenclature. And this is the list of the software tools that we reviewed. And in this reference, you will find all the algorithms that are used in each software to try to address the analysis of oxidized lipids. The level of annotation, the highest level of annotation we were able to reach was molecular species level and sometimes SN position level. But to give you an idea on the different approach compared to the use of DBs, I will show you first LipoStar, what we did in LipoStar. In LipoStar, the search for oxidized species occurs basically in unknown features after the detection of the classical non-modified lipids. And we apply a high throughput and simple way to detect potential oxidized species. For each unknown features, we see if the mass is compatible with the mass of a structure which is present in the DB, plus 1 oxygen, plus 2 oxygen, and so on. This will be the first list, broad list of potential oxidized species. When the MS-MS spectra are available, we can also search for compatible increments in the fragment ions. And sometimes we can also get which chain has been oxidized, depending on the spectra, of course. In this way, we generate a second list or more confident list of oxidized forms that can be again filtered to decrease the FACSI discovery rate, taking into account the presence of the parent lipid, because it is unlikely that one lipid is 100% oxidized. And if we work in the reverse phase, we can also take into account the retention time, because the retention time of oxidized species should be lower than the one of the parent. In this way, we can make the annotation of potential oxidized species in a few minutes. But reviewing all this software, the only one that was really developed only to address oxidized lipids was LPP Tiger 2. In this case, there are in silico oxidation algorithms that were developed in Dresden, and in silico fragmentation algorithms that were again developed. And in the end, this is the only method that can reach the type level in the annotation. What we have to address here is the time. It's more time consuming than the other methods, which are high throughput. So the idea, again, within the activity, research activity in EpilipidNet, the idea was to try to combine LipoStar and LPP Tiger, because LipoStar already calculates many of the data that are needed in LPP Tiger. And in this way, making the two software in the same loop, it is possible to have the benefit of the high throughput analysis, but with the benefit of a better annotation at the type level. So finally, in this in the last few minutes of this webinar, I would like to tell you something about our more recent research, that was the annotation of click chemistry-based derivatives. Click chemistry has revolutionized derivatization approaches for enhancing analytical performance in lipid tracing. And we were all inspired, I believe, by the works published by Thiele in 2019 and so on. And I'm reporting here one of the reporter he has used, the tracers, the C171, that allows to have a click reaction with alkene fatty acid in order to get this triazole here. What is important is that C171 bears a permanent positive charge, and this is very good for increasing the ionization efficiency. We have a nominal mass shift of 171 Dalton to monitor what is going on, and there is a neutral loss of 73 that is the results of the formation of the dimethyl ethylamine that seems to occur only when there is the clicked lipid, so probably the triazole has a role in that. These inspiring studies by Thiele were made in direct infusion. And again, my work here started from another idea, another request from Maria. And the idea was to try to integrate reverse phase liquid chromatography prior to mass detection. Our role was developing a software tool for a high throughput data processing. The way to work in click chemistry can be simplified and schematized in this way. We have to treat cells with alkene fatty acids, collect cells and extract lipids. Then we have to perform the click reaction and extract the lipids from the reaction mix in order to make, in the end, reverse phase analysis. From the computational perspective, in this specific case, we decided to go back to the use of a database of fragmented lipids. Now you know which is the problem. The problem are the structures, and the problems are the fragmentation rules. For the structures, we design our DB starting from these 5 fatty acids that should be virtually clicked already to make the complex lipids taking place in the DB. And we decided to take into account elongation, desaturation, conversion to sphingosine base, and conversion to hydroxyl form. The lipid builder was able to combine the 54 clicked with C171 reporter chain, native chains, and head groups, And in the end, we ended up with a database, a structural database of more than 200,000 clicked lipids, including species with only 1 clicked chain, 2 clicked chain, and 3 clicked chains. The lipid binder module was again improved in order to read and annotate and provide a name of species for species that were generated by these fatty acids. So it was not trivial, but in the end, we were able to generate all the structures we need to cover 15 main classes and 23 subclasses. That was the part of the structural DB. Now we need to code fragmentation rules. And this work was a massive work that started with a few alkene standards and alkene containing standards for complex lipids and a lot of in vitro generated data. And here we could have the advantage of monitoring the neutral loss of 73, but also to try to find a match with the masses from the database we generated already. Looking all these endogenous generated clicked species in the end, there was massive work to make the manual annotation of the MSMS fragmentation of the species, and the database was, the original database, the structured database, was at least useful to divide the compounds for the different classes to speed up the comparison and the annotation. Once the manual annotation was finished, the rules were coded inside, and the database of the structures was fragmented. So in the end, we had all these structures already fragmented. This massive work was mainly done by Palina, Gabriele, and Stefano. Among the nice results we obtained, I would like to show just this picture. This is one ceramide, a clicked ceramide, that was first annotated, identified by using the original fragmentation rule file, so the one that is used for non-clicked species, and there were only 2 matches. But after the application of our new fragmentation rules for clicked species, we were able to have 13 different matches. So that was a good result. And to conclude the presentation and also the work in the click, we, having now the database of fragmented species, we could reinvestigate all the endogenous labeled lipids that we could generate. Each entry of the identification was not a lipid, was one of the different adducts, like here, for the same lipid, for example. So we need to do adduct clustering and also the search for in-source fragment clustering. This was already available in LipoStar. And that was, of course, very important to attempt quantifications. We were able to annotate more than 700 clicked lipids. We could apply the Kendrick-Max defect plot, as usual, to reduce false discovery rate. We could use the retention time information. We were able to study in-source fragmentation of these compounds, and we were able also to annotate isomeric species. In this case, for example, we could find 2 isomeric forms that with 2 different retention times, and we realized that one was a ceramide with the clicked part in the fatty acid, and in the other side, the same ceramide with the clicked part on the sphingosine base. So in conclusion, in the analysis of low-abundant species, computational tools for processing and identification can really play a pivotal role today. And for the processing step, discriminating low-abundance peak of interest from noise is challenging, but tools are already available. And processing threshold, when applied to save time, are critical parameters, and testing to evaluate their effect is highly recommended. I'll show you why. For the identification step, spectral matching can still be very useful, but there is a general lack of standards to build libraries and define fragmentation rules. And for rule-based spectral generation, a rigorous understanding and coding of fragmentation rules is a very critical point, both for epilipids and derivatized lipids. So I will conclude again with thanking people working in my lab, in the DAISY lab, the collaboration with Mass Analytica people that help us adding everything we invent and develop in Lipostar. The collaborations that inspired everything I showed today, so the Imperial College in London, TU Dresden, Università di Aveiro, Bonn, Universität Bonn, Albert Einstein College of Medicine, Waters, University of Iceland, pharmaceutical companies, of course, EpilipidNet, Lipid Maps, the founding, and all of you for your kind attention.
Thank you very much, Laura, for the great talk. The first question was asked by the anonymous attendee. How do you find the parent unoxidized lipids if sometimes an oxidized product can be derived from several different fatty acid chains?
Okay, when we try to find the parent of unoxidized lipids, it can be that in the database we search for a match in the DB. So it can be that we can have more of one option. In that case, we provide a list of the options that are available. If the MSMS spectra helps us to reduce this list, because maybe we can see the fatty acids and we can reduce the number of the potential parent compound, we will show that with different scoring function.
Thank you. The next question was from Ed. Dennis?
Okay, great. Laura, that was a great and comprehensive talk on some challenging issues for all of us. I just a side piece. I note that you are using the word epilipids, and that seems to be referring to oxygenated fatty acids either alone or as part of complex lipids, as you very nicely explained. But others seem to refer to these as oxylipins, and historically we've all referred to these as eicosanoids or eicosanoids and related species for the 18 and 22 length fatty acids. Can you clarify the definition you're using for epilipids and how that relates to these other definitions that I've just described, so we know what complex lipids you're really discussing?
Yes, thank you very much, Ed, for this question, because due to the time, I was not going too much into that. And actually, this is very important because when I am using epilipids, usually it's just the general term to define everything is enzymatically and non-enzymatically modified throughout different reactions. But actually, from the computational perspective, what you're saying, like oxylipins or eicosanoids, or complex lipid in the sense of oxidized triacylglycerols or phospholipids, actually, they might have different computational solutions. What I was showing today is more on the oxidation of fatty acids in complex lipids, like again glycerol lipids or phospholipids and so on. But for oxylipins and eicosanoids, I still believe that it is very important to have these structures also already coded and present in the databases that people are usually used. And indeed, they are also present in the Lipid Maps database because they should be always in the general panel. It is not a combinatorial explosion. This should be considered in the regular way to work of the software, okay? The point is that when we start studying the epilipid in the terms of the complex lipids that might be oxidized in different chains and so on, the idea of making a single DB with all the potential structures is not the way to go because everything will be quite slow. To reply to your question, my use of epilipids in the first part was the most general term, so including everything, but the solution I was showing today are more efficient for complex lipids. For oxylipins, eicosanoids, I would say that it's better to use what is already available, so experimental fragmentation routes or species, and try to stay closer to the experiments as possible.
Great. Anyway, terrific view.
Thank you.
Good. There is another question in the Q&A from Xue Heng Zhao. Okay, I will read it out. So will the PASTA tool take open source MS data file formats or vendor specific files such as raw files from Thermo?
Actually, both. We read instrument data format from Thermo, Waters, Agilent, Bruker, using converters, and sometimes we have for Waters and Agilent, we can directly read the files. For others, the user has to download a patch from the vendor, but then it works. And they can also use MZML format.
Good. And then there is a question from Val.
That was great, Laura. I've got a question about the oxidized lipid software. Obviously, that's really interesting to the work that I do. And I just wanted to find out, like, you know, by now, I guess it's been used extensively across many data sets. And do you find that particular structures show up more often than others, as you know, and are more abundant than others? You know, is there kind of signatures emerging that kind of reflect particular biological processes? I guess particularly like if enzymes are involved, you're going to see certain ones coming up. I just wondered if you see some of this in the data that you get from this tool.
Oh, no, I do not have an extensive, amount of data to do this analysis. I was more focused on trying to get the largest annotation that we could get, but then the software is in the hands of the groups that are using, and they are not sharing with me the final results. So unfortunately, I do not know, but if you have nice results to test, I will be glad to go deeper on that.
Yeah, that would be great. Although we tend to use targeted assays, so you need kind of like an MS-all type approach for this, I presume, don't you? Where everything is being scanned and fragmented rather than targeted.
Yeah, we need that. Yeah, usually we work with
yes,
MS.
So I don't have that sort of data really. Okay, thank you.
You're welcome.
Then there is a question from Jean-Marie.
I wanted to know if there is because I never quite used the software. I'm shameful about it, but is it easy to extract the data, the filter data that you can extract and download that to the GNPS website, like an easy way, like NZMind does it nowadays? Is it possible?
No, not yet. No.
Yeah, it'd be nice to implement it.
Thank you for suggestion.
All right. No problem. Very nice. I will use it pretty soon.
Thank you.
Thank you so much.
I would like to ask a question.
Sure.
And this is about let's say the first part of your talk about the gap filling and the missing values. Yeah, it becomes a very big topic, right? In the omics data in general, and lipidomics, metabolomics in particular. Are you planning, or maybe it's already implemented in some way, to actually address these different types of missing data, you know, all this missing at random, missing non at random, and all this kind of things? And yeah.
Well, at the moment in LipoStar, we developed an algorithm to automatize the definition of some of these thresholds, like the conversion threshold, at least to reduce the manual intervention if someone is not trained to decide what is noise and what is not. Other options are available in trying to, fill these missing values. There is the gap filling, but there is the other methods that works with the the average, weighted average, and so on in a column. There are many different algorithms that can be used. There is the NIPALS algorithm that is used a lot in chemometrics. At the moment, what we do is to provide 2-3 of these methods in the multivariate statistical analysis page, because to me it's very important to understand how much these missing values can affect the final results I see. So since to make PCA or a PLS, really it's a matter of a few seconds, my suggestion is to test the effect of the algorithms that are variably filling these missing values. No? If the results doesn't change so much, that means that we are not missing too much and there are not so many. Otherwise, it's better to revise the overall workflow. Another important point is the filter by frequency, because it is usually accepted that maybe we can make a frequency filter, to exclude all those variables that have a number of missing values higher than the 80%, okay? But still, this is too flat, because in this way, probably we are going to miss a lot of low abundance species. So at the moment, it is really also data dependent. It is important to provide fast tools to evaluate the effect of those missing values. And I am trying to always to push people to test more than one method to see the effect, especially if they want to go to low abundance species.
Thank you very much, Laura, for the answer and for the great talk today and for the great webinar. And with this, we are at the end. And I would like to thank all of you for attending and asking questions. Thank you very much.